In this video, we're going to delve a little bit more into the ageostrophic wind. We've been talking quite a bit recently about the ageostrophic wind, as it is a vastly important element to our transverse ageostrophic secondary circulations. But what is all contained within the ageostrophic wind? So let's go ahead and take a look at our full ageostrophic wind vector, VAG. We know if we go back to dynamic meteorology, can say that this is equal to k hat over f cross dv dt, total time rate of change of our velocity vector. And so we can expand out this total velocity vector such that we have k hat over f cross then three terms: local dv dt plus the advection of wind by the wind in the horizontal, and then the advection of the wind in the vertical. And so if we replace the V's with the geostrophic wind, so we're going to replace V with VG, then we can substitute in and get our equation for VAG based on the geostrophic wind. K hat over F cross dVg dt plus Vg dot del Vg plus omega dVg dP. And so it turns out that these three different parts combine to form the ageostrophic wind. And we want to look at two of these elements in a little bit more detail to unlock some of the things that are contained within this ageostrophic wind. And so we are going to look at our first term here, which is our local wind tendency. And will allow us to determine the isobaric wind. And then we are also going to look at our second term here. And our second term is going to allow us to look at the inertial advective wind. And then we're not going to do anything but this third term is a convective term that is part of our ageostrophic wind. And so let's go ahead and start with this concept of the isobaric wind. And so if you wanted to look up, we could look up what isobaric means. And isobaric means basically lines of equal pressure fall or rise, right? So of equal change in pressure or heights. And so we can call out here just our isobaric portion. And so we can say that our isobaric wind, V isol, equals k hat over f cross dVg dt. Now here, since we're using the geostrophic wind, we could substitute in for geopotential height such that we can change our equation or alter it to be k hat over f cross ddt of the quantity k hat over f cross del phi, which will leave us with minus 1 over f squared del d phi dt. And so ultimately, our isobaric wind is going to relate our vertical motions through our convergence and divergence of the isobaric wind. And so if we go ahead and take the divergence of our isobaric wind, we're going to take del dot v isol such that we're going to get minus 1 over f squared del squared d phi dt. And again, what is d phi dt? Right? This is chi. This is our height change. We could also do the same thing for pressure falls. And so we could make a similar argument and say it equals minus 1 over rho f squared, if we're going to do our conversion properly, del squared dp dt. And so whether we have pressure falls or we have our more classic upper level height falls, the divergence of our isobaric wind is going to help us determine where we're going to see convergence and then thus rising motion. And so if we have del.v isal less than 0, that means then our term for our pressure falls is going to have to be also less than 0. The whole term would be less than 0, such that we know we have the minus sign, so that would make it less than 0 already, so that the combination of the rest must be less than 0. Rho will be positive, f squared will be positive, del squared, the Laplacian, will change the sign, such that we know that then we should have dp dt also less than 0. And so that means pressure falls where we see convergence of the isobaric wind. And so subsequently, pressure falls are where we're going to see rising motion. And again, none of this should be surprising in the context of everything we've done this semester, but that this comes out of this ageostrophic wind. And so it's important to remember. Similarly, we could do the same argument for that divergence of the isobaric wind being where we see pressure rises, we're going to see sinking motion. And what we're really observing here is the development of where our new low pressure and high pressure are going to be, as we know they constantly reconstitute themselves through time. Moving on to the inertial advective wind, this one is also a bit interesting and helps us to figure out a little bit about what's going on with our difluent areas of troughs. So let's go ahead and first write out some of our inertial advective equations. So the inertial advective wind. And so here we're going to call this VIA, and this equals our K hat over F cross. And now I am going to write out the terms here that we're going to have in both our I and J components. And so remember that this is the advection of the wind by the wind. And so our I component is going to be UG, DUG, DX plus VG, DUG, DY, I hat, plus UG, DVG, DX, plus VG, DVG, dy, J hat. And there's our full inertial advective term. Okay, well this is great. But let's go ahead and look at a drawing here related to our inertial advective wind. Let's go ahead and look at a difluent zone. And so maybe this is 300 millibars, and we have our normal difluent zone, 912, 924, 936. And so what we're really curious about here is what's going on in kind of this difluent zone here. And so we're going to look at it just right along this 924 contour here. And so we can pare down our full equation here to look at just a subset. And so we're going to look at our inertial advective component here being VIA as equal to K hat cross or over F cross UG DUG DX. And so we want to assess, we know that our UG here is going to be stronger here, weaker here. And so now we want to assess UG DUG DX. And so we can do that. So faster here, weaker here as we go along in our positive x direction. So let me first indicate here our x and our y. And so with our dug dx term, right, what's happening? Ug is decreasing as we go in increasing x direction. Times then, Ug is still positive, so that overall term is going to point back to the west. This is our Ug dug dx term. Okay, again, because our wind speed is decreasing as we move in the positive x direction times a positive value. So dug dx is less than 0, Ug is positive, so that this whole vector is pointing to the west. But now we need to do our crosshat. K hat cross V, right-hand rule states that our inertial advective wind is going to point in which direction? That's correct. K hat goes up first. Curl your fingers to cross in the direction of Ug dug dx, and your thumb is going to point towards the south. And this is going to be most pronounced right here along this 924 line. And so what that ends up meaning is that we are going to get convergent flow to the south and divergent flow to the north according to our ageostrophic wind. And so what this means for difluent areas is that the whole difluent area is not necessarily good for divergent flow. It is only this area to the north that is really good for divergence. And that's because divergence in natural coordinates has two elements. So just like we can do vorticity in natural coordinates, we can also do divergence in natural coordinates. And so we'll say div here equals dv ds plus v d alpha dn. And this first term here is speed divergence. And the second term here, this is where we get that term difluence or diffluence, depending on how you talk about it, potato, potato. So in general, we would consider this pattern that we drew up here to be difluent. Our height lines disperse as we go to the east. Difluent pattern here. Oftentimes, though, we talk about this difluent pattern as being good for divergence in and of itself. But as we see in natural coordinates, we actually have this speed divergence term that is a part of our overall divergence. And what is happening to the speed in this picture? That's right, it's decreasing as we leave and go into the difluent area, which that is going to cause convergence of flow in general. And so the question in this whole difluent pattern is what's going to win out? Is the speed divergence going to win out, or is the difluence term going to win out? And the only one that we know kind of for sure is this northern side in the northern hemisphere here pattern of our diffluence, where we know that that divergence should win out even when considering our speed divergence and its effect on the inertial advective wind. So be careful when we're talking about difluent patterns. Difluent patterns in and of themselves may or may not help the divergence of the pattern. And at this modern date, when we no longer have to rely on just visual cues on our maps, but where we can actually calculate things, it would be much better to actually calculate the divergence in an area to better know what's going on in the atmosphere. So this was a bit of a look into the various terms that come from our ageostrophic wind that we've been talking a lot about, and there's a couple of different factors going on in there, but when we break this ageostrophic wind down, we find some really interesting aspects, especially related to the isobaric wind and the inertial advective wind. Thanks for watching.